Take a look at a decimal like 0.2 and compare it to 0.200. Because 3 digits take up more space than 1, the human brain often assumes that 0.200 has a higher value. This is the zero dilemma. When we break them down by column using a place value master matrix, we can see exactly what these numbers hold. We have 0.2, 0.20, and 0.200 stacked vertically, separated into their specific place value columns. Every row contains exactly 2/10. Those trailing zeros on the far right have no weight. They don't change the fact that the core quantity remains identical across all three numbers. But if you slide a zero between the decimal point and the digit to create 0.02, the zero pushes the 2 out of the tenths column and into the hundredths column, reducing its value by a factor of 10. Correctly reading a decimal relies on analyzing column weight rather than counting the total number of digits on the screen. Methodical. This logic allows us to track down a complex coordinate like 4.185 on a standard number line. We start with the broad scale between the whole numbers 4 and 5. We divide this unit into 10 equal tenths. Since our target contains 1/10, we look specifically at the segment between 4.1 and 4.2. The camera then magnifies the space between 4.1 and 4.2, revealing a new 10-part runway of hundredths. Our target has 8 hundredths, so we focus on the segment between 4.18 and 4.19. One more zoom into the gap between 4.18 and 4.19 reveals the thousandths marks. We count 5 small marks across this final microscopic track to find the exact position of 4.185. Every additional place value represents a 10 times deeper spatial magnification. You can locate any decimal by systematically zooming in one decimal place at a time. This spatial logic helps us avoid traps where numbers like 6.456 and 6.465 are placed next to each other to confuse the eyes. We compare these by evaluating the digits from left to right, starting with the highest place value column. Both numbers have 6 units and 4/10, leaving them in a tie. In the hundredths column, the first number has 5 hundredths, while the second number has 6 hundredths. Because 6 is greater than 5, 6.465 is the larger value. Once this difference is established, we can stop comparing. The digits in the thousandths column cannot change the result. Systematic column checking ensures you are evaluating the hierarchical value of the digits rather than the optical pattern of the number. We can use this same comparison method to find which of these 4 neighbors, 0.9, 1.01, 1.1, and 1.11, is physically closest to the landmark integer 1. Here is how these candidates sit on a track relative to the number 1. Based on the left-to-right comparison rule, which of these has the shortest distance to 1? Pause and make your prediction now. Measuring the distances shows that 1.01 has a gap of 0.01, making it the closest neighbor to the integer. Spatial proximity is determined by the value in the nearest right-hand column. Small differences in these columns dictate the physical distance on the line. Now try combining spatial zooming and column checking to solve a final riddle. Look at these 3 neon decimal candidates. Analyze the place value columns and determine exactly which one is closest to the whole number 4. Drop your final choice in the comments. You can now locate coordinates using spatial zooming and resolve comparisons by checking place value columns from left to right. Relying on place value mechanics instead of visual intuition is the most reliable way to avoid whole number bias. See you in episode 5.